Hi everyone, my name is Ademola Ibironke. I am a graduate student of Lamar University. This is a presentation of the impact of storage zones on mainstream. Um, this presentation is done in conjunction with my colleagues Vandan Kadia and Saha Sonto. I am going to be introducing the concept of this project. I'm going to quickly talk about what the problem is, what we are trying to do, concepts, explain the models, and talk about the plots and briefly mention the summary. So this project is a reproduction of a paper that was done by Chapra Stephen and Runkel Robert on modeling the impact of storage zones on dissolved oxygen. We are using the RK45 method, a numerical method to solve this problem that was originally done analytically. Some of the main definitions of this project include the main channel, which is the body of water, in which water flows downstream and also contains some pollutants. The storage zone is the area of stagnant pockets of water and porous stream beds. We are going to be talking about the dissolved oxygen in the stream, which is the amount of oxygen present in the stream. The biochemical oxygen demand, BOD, is generally how much dissolved oxygen is needed to break down organic matter in water. Our conceptual model shows our point source in the main channel, as well as the direction of the flow of water. It also shows the relationship between the main channel and a storage zone, indicating that some level of chemical reaction is going on between the two. The second conceptual model is just more details about the flow of water and pollutant in the stream. It also shows the point source, shows where we have storage zone, and that some chemical reaction is going on between them. Some of the assumptions in this project is that we are assuming that the shape of the medium is constant, the shape of the main channel and the storage zone are constant, that the stream flows in a predominantly by advection. Another assumption is that temperature in the storage zone and the main channel are the same. But a critical assumption in this project is that re-ration in the storage zone is negligible. Quickly, let me go over some of the models. So we have two models showing what happens what happens in the main channel when there is a storage zone, what happens to the BOD, as well as the dissolved oxygen, and what also happens when there is no storage zone, around the main channel. So our models, the first model and the second model, are going to be showing that. But that part of this project is going to be presented by, the rest of this project is going to be presented by both of my colleagues, Ovi and Vanden. I'm going to allow Ovi to go ahead and explain some of our governance equations and the parameters we used in this presentation, in this project.
Hello everyone, my name is Ovi. I'm going to talk about governing equation. There is four equation for LS, which is for BOD, for storage zone, and also have dl by dx, which is change BOD in main channel, and ds for DO in the storage. Our fourth equation is dd by dx, which is for changing or changing DO for main channel, and we are going to talk about our initial condition, where is L0 is 10, which is like a BOD concentration at the point source, and DO is 0, which also BOD DO for at the main source. And for our code, we are going to load library, import the numpy as an np, and we are going to solve the IBP function. And for input the parameter, we have some value which is already given in the paper, and we are going to write down in the in the Jupyter. And here for model 1, the main stream without storage zone, the function for solving ODES without storage zone, um, we got like we have L equals to y0 of 0, D equals to y0 of 1, which is for L is for BOD and D for DO. And we got two equation before. We have four equation in the paper, which is like one is first one is for a storage zone, and third one is a storage zone. Third one is also a storage zone, so we are not taking these two equation because uh, we are going to modeling the main stream without a storage zone. And also one more thing, the alpha is here is 0 because alpha equals to the constants, the rate for the exchange rate for main channel to the uh, storage zone. So here we are going to like take two equation, where is dl gx equals to minus kd, and dd dx. We just put two equation and get, and we are calling the function into solve IBP, solve the governing equation for input parameter. And here we can use method rk45, and here also the t span equals to x span, cause in the paper there is no time, so we are taking the distance, and y naught equal to y naught. This is according to the rk45 method. And for results, the main stream without storage zone, we can print the masses and the number of function evaluation is 68, and the success is true. And now we are going to convert of array BOD into the list of L, and convert value of array DO list as D. So we have to now we are going to get the value of oxygen for OX equals to empty bracket, because what we find it will get into the bracket. And we are using for loop j in range length d, OS equals to 8 minus dj, for formula of DO equals to O saturated minus oxygen.
Okay, thank you, Ovi. Hi, I'm Managadia. Now I will explain the further model, that is model 2, which is mainstream along with the storage zone. So here we did the same for the mainstream, like without storage zone, we made a function, we gave the name is ODS in the storage zone. So here we have four equations to solve, because there will be the value of LS and DS in the storage zone with the alpha 2. So we'll take three values and get solve the four equation. Okay, for that we use the solve IVP function to solve the differential equation. So here our t span will be the x span, we are calling function, Then y0 is the initial condition. We are going to use the method RK45 to solve the differential equation. So our T equals will be the XX. Okay, so now you can see the results, that is with the mainstream along with the storage zone. So the number of function evaluation is 68 and we successfully carry out the results. Okay, now we convert the array of y0, which is the value of BOD, in the list, and then for the DO we did the same for y of 1 into the list for D. Then we find out the oxygen value of oxygen for each value of the DO deficit from the equation, that is the DO deficit equals to oxygen saturated minus oxygen, and here the oxygen saturated is 8, which is given, and we just convert the distance into the list. And now we'll find out the concentration of BOD and DO in the storage zone only. Okay, so here we're going to use the equation of LS, and we will find the values of LS, and then we done for the DO, and we're gonna find out the DO by using this equation, the DS equation. But here we have the DS is dependent on two variables, which is DS and LS. So we need to take the JEEP object. So JEEP will combine two lists and will take value according simultaneously from two lists at a time. Then we did the same for oxygen. We find out the oxygen values of oxygen. Then we plot the graph. So you can see in the plot there is the breaking line, magenta line is showing the value of BOD in mainstream without storage, and the continuous red line is showing the value of BOD in mainstream with storage. So there is the difference between two lines, and also the breaking lines, the black breaking lines showing the oxygen in the mainstream without storage, and the yellow continuous yellow line is showing the value of oxygen in the mainstream with storage. So there is a difference between two lines. So the BOD in the channel without storage is faster than the BOD count decomposition rate in the red line with storage. And here you can see that there is the continuous magenta line is the BOD in mainstream without storage, and the continuous black line is going in mainstream with oxygen. For oxygen in the mainstream without storage, and that is the breaking red line is showing the value of oxygen in storage zone, and the breaking blue line is showing the value of BOD in storage zone. So there is the difference between the two LS and LS in the storage zone and LS without the storage zone. Okay, so we can find it out by this two plot, that the BOD decomposition rate was shown to be the slower in the stream with the storage zone compared to the without storage zone model, and the DO decomposition rate we can see here. This is going down, and it will go back to the saturated level for the DO. So that's the storage. The benefit of providing storage zone is that they reduce the velocity of the flow and give the residence time to the flow for the reaeration in the mainstream. So thank you for watching our video.